This is problem 726, and we solved this problem in another tutorial by using online a database that had the properties of subcooled liquid water. What I want to do now is go through this, what I call the more theoretical way to solve this problem. And this is something that you should become familiar with, and you will need to use this for solving some problems, so make sure you learn it. But this is useful if you do not have access to property tables like we do for water. And so this goes back to the fundamental property relations for chapter 9. So we've got, just to refresh yourself, we've got liquid water coming through this turbine, and it exhausts at 1 atmosphere. We don't know the temperature. We're asked to calculate the power output if the efficiency is 55%. And we're also asked to find the outlet temperature of the water. Remember, when we solved using the steam tables, the online steam tables, we didn't care that whether or not it was compressible or not. The steam tables assumes that it's not an incompressible fluid, or it is a compressible fluid. Here we're going to need to invoke the assumption, if we're going to solve this theoretically, we're going to need to invoke the assumption that water is a compressible, liquid water is an incompressible fluid. So again, we start with this fundamental property relation, equation 6.9 in your textbook, which says dH is equal to TdS plus VdP. And what we're going to do is we are going to say, okay, we're given the efficiency, and remember this efficiency is with respect to isentropic operation. So we're going to jump immediately to the isentropic case. So the isentropic case would be where ds is equal to 0. We're going to apply this equation to the turbine, and we're going to say it's isentropic, so ds is equal to 0. The input minus the output, or from the input to the output. So that leaves us, if ds is equal to 0, that leaves us dH for the isentropic case, this whole term goes away, is equal to V dP. All right. So if it is applied to a subcooled liquid, what can we say? Well, the volume is usually constant, right? The volume's constant. We're assuming it's an incompressible liquid. There's no equation to state volume is constant, so we say that volume is constant there. And what we get is that delta H, we integrate this from now state 1 to state 2, so we get delta H for the isentropic process is equal to volume, which is constant, and what's the integral of what's the integral of dP from P1 to P2? We are going from P1, 5 atmospheres, to P2, which is 1 atmosphere. That's just delta P. So our isentropic work is equal to V, or molar volume, specific volume of our water, times the pressure difference, all right? Because remember, for a turbine, the energy balance reduces to work is equal to delta H. So now what we can do is we can solve for the isentropic work. Right? What we have to do is we have to look and we have to figure out what's the specific volume we're going to use. We already know the pressures, right? So all we need to do is figure out the specific volume. So what I would do, I would go to the saturated steam tables and look at 15 degrees C. Right? Our water coming in is at 15 degrees C. Let's get the molar volume, or the specific volume I should say, at 15 degrees C, and we are going to assume that is going to be constant throughout our process. That is, the density of water does not change in our process. It's incompressible. We look this up, we get the specific volume is 1.001. And remember that your steam tables in the back of your book use centimeters cubed per gram as the unit. Also remember, if you're using MathCAD, gram is GM. And if you take a look at your steam tables, you'll see that if you read down the saturated liquid volume column for different temperatures, you'll see that that changes very little, right? It's changing in the thousandths decimal place. So we plug this in and we solve for the isentropic work. We solve for the isentropic work and we get minus 0.406 kilojoules per kilogram. We then take our efficiency that was given to us and we multiply by the isentropic work and we get a value, a real work that's produced of 0.223 kilojoules per kilogram. And if you are remembering what you did in your previous problem using the subcooled liquid properties that you looked up online, you'll see you got the exact same answer to 3 decimal points. So this is actually seems to work pretty well, this method. We start with a fundamental property relation, isentropic, TDS falls out, we're left with VDP. We assume, because it's a liquid, we assume that V is constant, and so we get delta H is equal to V delta P, which is equal to the work. Look up V, calculate work for isentropic, calculate work for real using the efficiency, and that is what we get. Now, they also ask us to calculate the temperature. And so remember, with the online property tables, we could just enter in the values and have the little database look it up and spit it back at us. But here what we're going to do is we need to pretend like we don't have access to that. So what do? Well, to calculate the change in temperature, we can go to equation 627 and we can integrate that equation. And so I didn't write down equation 627, but you can follow along in your textbook. We can integrate that equation for dH, and we make the following assumptions. Number one, or letter A, we assume that specific volume is constant, so V stays constant. We also are assuming that Cp, the heat capacity of our water, is constant. That's a pretty good assumption. We're also assuming beta is constant. Right? And we're also going to assume that the product of beta times T is constant. Now, is that a reasonable assumption? Well, if you remember back in chapter 3, if I'm paging back in my textbook in chapter 3, we look at the value of beta. Remember, beta is the volume expansivity. That is, how does the volume, the specific volume of liquid water, change with respect to temperature if the pressure is constant? Well, we just looked at the saturated liquid volume and we saw that it barely changes with respect to temperature in our saturated steam tables. So a small number, beta, first we assume beta is constant. That's fine. But also, beta is a very small number. And so if you look up some values of beta, you'll see that it's 10 to the minus something something. So what we can assume is that the product of beta times temperature, and our temperature is only 15 degrees C or 288 Kelvin, that is also going to be much less than 1. So when we do that, we get equation 725 that can further be simplified to this equation right here. So I haven't done all the derivation, but I encourage you to do that derivation and that inspection of these equations on your own. Make sure that you can do this kind of reasoning, because there will be several other times in subsequent courses where you need to make these kinds of assumptions to be able to do a calculation, these simplifying assumptions to do these kinds of calculations. So what we end up with delta H is equal to Cp delta T plus V delta P for a liquid. And so we can solve for delta T. And so what I've done here is I then look up the heat capacity of water, and I forgot it for the the moment, and so I looked in the back of the book. Heat capacity of water is about 9.069 times R. So if you do that, it's 75.4 joules per mole Kelvin. And then remember, we are dealing in mass units, so make sure you are careful with your units. Don't just plug numbers in and hope the units magically work out themselves. But I need to divide by the molecular weight to get my CP in kilojoules per kilogram Kelvin. And this is what we are used to seeing for the heat capacity of water. Then I solve that equation for delta T. So delta T is delta H minus V delta P over Cp, where delta H for my energy balance is the real work. All right, it's the real work. So I plug my numbers in, and what do I get? Again, I'm correcting for, I just left it in moles, so I'm correcting for the units here. We get a delta T of 0.044 Kelvin or 0.044 degrees C. And so our final temperature is 15.04 degrees C. And if you remember, when we were using our online subcooled water properties, we got a final temperature of 15.04 degrees as well. So using this method, you see that the assumptions work pretty well compared to the work that we did with the online steam tables. I kind of like using the online steam tables. They just give me a little bit better feeling. You feel like you aren't making so many simplifying assumptions, although these are really good assumptions and valid assumptions. It just feels a little bit better to me to use the actual property tables. But what you should take away is that you can do this problem even if you have no property tables. So what did we find? What did we have to look up? All we had to look up was the specific volume of water and assume that was constant. And then we had to look up the heat capacity of water and assume that was constant. And for this condition where we have a liquid water going through a turbine like this, we got values that were pretty much exactly the same that we had using our property tables. So temperatures, and another thing to note, subcooled liquids, they really don't change temperature that much when they go through pumps and turbines where the pressure changes are not super large. Also, I wanted to note there's an error in your publisher solutions. They do the problem correctly until they get to this point. They calculate a delta T, but then they subtract it. So they actually get something like 14.96. That is incorrect. They did not apply their delta T correctly. So the answer is 15.04 degrees C.